So this is the continuation of the first part of the discussion about shear and moment in beams. For sample problem number 3, establish the shear and moment equations for the beam shown in the figure. Draw also the shear and moment diagram. Okay, so for this beam, okay, so this is a simply supported beam. Okay, so this is 18 feet and it has a trapezoidal distributed load, no? So the intensity of the load here is 2 kips per feet, and here, no, at the another end, no, so the intensity of the loading is 6 kips per feet. Okay, so to solve this problem, class, okay, so again, our first step, no, is to solve first for the reactions, no, in the supports, no, of the beam. So in this case, this beam, this is supported by a roller here, no, and at the other end, it is supported by a hinge. No, so we are going to solve first for the reactions, no, in those supports. Okay, so this is the free body diagram, okay, of this beam. Okay, so for the support at the or the reaction here at the roller support, so this will be the reaction. Okay, so since that is a roller, no, so we will only have reaction force here, and this will be perpendicular, no, to the surface where the roller is leaning. Okay, so in this case, this surface, this is horizontal surface, no, so meaning to say, the reaction force here, class, will be vertical. Okay, and also, class, for hinge, we know that for hinge, there supposedly there's two reactions here, right? One horizontal reaction and one vertical reaction. But in this case, in our beam, no, so there's no horizontal loading here. So the horizontal reaction here will just be 0. So there's only a vertical reaction here. So this will be the reaction, no, for the hinge. Okay. And then, class, since we have here a trapezoidal loading, no, so to solve this, no, we can convert it into its equivalent point load, no, so we can divide this trapezoidal load into rectangle, no, so this will be the rectangle, okay, and then into triangle. Okay, so just to solve, no, the equivalent point load, okay, of each shape, no, and so that we'll be able to ano then to determine their location, no, of each point load. So for this rectangle, its equivalent point load, class, will just be the area of this rectangle. So the area of this rectangle, so its height is the intensity, which is 2 kips. So this is 2 kips. Okay, so this is 2 kips, class, and its base, okay, its base, class, this is 18 feet. So this will just be 2 times 18. Okay, and 2 kips per feet times 18 feet, that is 36 kips. No, so this will be the magnitude of the equivalent point load. And this equivalent point load, this is, since this is a rectangle, okay, so its location will just be at the center, okay, of the rectangle. So in this case, class, if this is 18 feet, so this equivalent point load, this is located half of 18 feet, which is 9 feet. Okay, now for the triangle, so for the equivalent point load of the triangle, this will just be the area, okay, of the triangle. Okay, so in this case, class, the base of the triangle, this is 18 feet, and its height, this will be 6 feet minus 2 feet. No? So for the height of the triangle, so that will be 4 feet. Okay, so solving for the area of this triangle, this will just be 1/2 base times height. So this will be 1/2 times 4 kips per feet times 18 feet. Okay, so the answer here, class, will be kips, no? So 1/2 times 4 times 18, this is 36. Okay, so this is the magnitude of the equivalent point load of the triangle, 36 kips. Okay, and class, the location of this point load, no, so if it's measured from the tip of the triangle, so from here to here, okay, so this distance, class, is 2/3 of the length of the triangle. So in this case, the length of the triangle is 18, so this will be 2/3 of 18, no, which is 12 feet. But if you are going to measure this location, no, from the other side to the equivalent point load, this is 1/3, okay, of the length of the triangle. which is 1/3 of 18. What is 1/3 of 18? 6, no? Okay, but in this case, this is measured from here, ha? Okay, so this is 2/3 times 18, so this is 12 feet. The location, no, or the position of the equivalent point load from the left. Okay, so from here, class, we're going to solve these reactions. Okay, so we can sum up forces or sum up moment or take moment here at this point, no, so that R sub 2 will be cancelled and the only unknown will be R sub 1. So we will be able to solve for R sub 1. Okay, on the other hand, also class, no, we can take moment here, no, at R sub 1. Okay, so that R sub 1 will be cancelled and we can solve for R sub 2. Okay, so here class, no, that is what we are going to do. We are going to sum up or take moment here, no, at the point of R sub 1. Okay, so taking moment here, okay, so R sub 1 will be cancelled. So for this equivalent point load class, so this is 36 and its moment arm class is 9 feet. Okay, so taking its moment class, its rotation will be clockwise. That's why it's positive here, ha? So our convention here, positive for clockwise rotations. So that is the moment, ha, of this equivalent point load, 36 times 9. Okay, and for this another equivalent point load, so this is also 36, and its moment arm about this point class is 12 feet. So its moment will be 36 times 12, and its rotation also class is clockwise. That's why it's positive here. And then for this reaction, so its moment about this point, it will be R sub 2 times the moment arm, which is 18 feet. So its rotation class will be counterclockwise. That's why it's negative here. So this will be equal to 0. So we can directly solve for R sub 2. Okay, so solving for R sub 2, if we input that in your calculator, okay, 36. So R sub 2 times 18, now we will just transpose it to the other side so that it will be positive. So this will be 36 times 9 plus 36 times 12. Okay, divided by 18. So this will be 42 kips. Now for the another reaction, okay, which is R1, okay, we can sum up forces vertical here since R2 is already known, no? So we can already use that. So summing up forces vertical, positive force will be the upward forces, no? So R sub 1, okay, so that will be positive, minus 36, downward, minus 36, this is also downward, plus R2. So we just substitute the value of R2 here, class. Okay, so solving for R1, this will just be 36 plus 36 minus 42. Okay, so that will be 36 plus 36 minus 42. This is 30 kips, no? Okay, so now, after we solve for the reaction of the supports class, no, we can now proceed to our next step, no? So this is already for the shear and moment equations or functions. Okay, so what we're going to do first is divide the beam into segments. Okay, so that the loading within each segment is continuous. Okay, so from here, class, no, as we know, this beam, so its loading class, no, it starts from here, okay, and it continues up to this point. Okay, so meaning to say, class, no, so from here to here, no, so this will be one segment. Okay, so class here ha, the endpoints of the segment are discontinuous of loading. No? So the loading here class is from here, no, and ends here. Okay, so this will be one segment from this point up to this point. Okay, so class, from that segment, we are going to ano ha, we are going to cut a section anywhere. No, anywhere here. It can be here, can be here, can be here, it can be here. Okay, and the distance, no, from the leftmost part of this beam to the section where we are going to cut this beam, okay, the distance will be x. Okay, so let's say this is the cut section. Okay, so we are going to consider here the left segment. Okay, so let's say we cut the beam here at this section. Okay, so this will be the left segment. Okay, so class, the distance, okay, from the leftmost part to the section where we cut the beam, that distance, we will put x here. So this is distance x. Okay, so from here, class, no, the loading, no, at the segment, okay, where we or the segment that we consider here, class, which is the left segment. So the loading here, class, is this trapezoid, no? And we know that the rectangular load, class, okay, so we divide this into rectangle and triangle, right? So the rectangle loading here, class, will be just constant, no? So it will still be 2 kips per feet here. Okay, but for the triangular load, so this is varying, no? So we don't know the value, no, or the height of that triangle. So we just name it as W, ha, here. Okay, so we are going to solve, no, the value of this W. Okay, so we are going to solve that later. And of course, we have to include here also the reaction force, okay, for the support, no, here, no. So the reaction here, class, is 30 kips. Okay, so class, also for the loadings here, class, no, we are going to convert them into its equivalent point load. So for the rectangle, the equivalent point load of the rectangle is just the area, no, of the rectangle. So the area of the rectangle will be base times height. So in this case, the base, okay, which is this distance, so this is x. Okay, so this is x, and then its height is 2 kips per feet. That's why for the magnitude of the equivalent point load, so that will be the area of the rectangle, that is 2 times x. Okay, now for the triangle, okay, the height of the triangle is W, and then the base is x. So for the area of the triangle, 1/2 base times height, so that will be 1/2 W times x. Okay, so from here, class, the location of this point load for the rectangle, no? Okay, so this is at just the center, okay, of distance x, which is x over 2. And for the distance or the location, class, no, of the equivalent point load of the triangle, okay, so from here, class, this is 1/3, no, of the distance x. So that is 1/3 x, or x over 3. Okay, so from here, class, no, here, we cut the beam at this section, no? So at this section, class, we are going to put here the internal shear forces and internal shear force and internal moment. Okay, so we are going to, um, put here the positive convention for shear. So for the positive convention for shear, class, no, it should cause this segment to rotate clockwise. So in this case, it will cause the it will cause the beam, okay, or the segment, okay, this segment to rotate clockwise. So this will be the positive assumption for shear. Now for the moment, class, okay, so for the positive assumption for moment, it should cause the segment not to bend concave upward. So in this case, class, if it will rotate this way, no, it will press, no, if the moment will the direction, if the direction of the moment is this way, so it will cause the uh, beam or the segment of this beam to be concave upward, no? So that is the positive assumption. Okay, so from here, class, we are going now to solve first, no, for the value of W. Okay, so for the value of W, class, we are going to use proportion here. No, so we are going to use the proportion of this larger triangle, okay, and this is smaller triangle. So they are similar triangles, so therefore we can use proportion here. Okay, so from here, class, so the base, okay, or the height, no, the height of this smaller triangle over its base will just be equal to the height of the larger triangle over its base. Okay, so therefore, this will be 4 over the base, no, of the larger triangle, which is 18, equal to the height of the smaller triangle, which is W, over its base, which is X. Okay, so from here, class, we can solve for W. So W is equal to 4X over 18. So we are going to use this value of W, and we are going to substitute that here and here. Okay, so we can now solve, no, the shear and moment equations here, class, using equilibrium equations. Okay, so class, the equations that we're going to establish here, okay, it will be it can be used, no, from any distance x, no, or for any distance x from 0 to 18. Okay, since that is the length of our segment here. Okay, so from here, class, no, let's solve the shear equation by summing up forces vertical, no, from this segment. Okay, so summing up forces vertical is equal to 0, and our assumption will be positive for upward forces. So this will be 30 minus 2x minus 1/2. So the value of W class is 4x over 18 times x minus V. No? So this is the internal shear. So solving for the internal shear force class, so this will be 30 minus 2x minus, so simplifying this class, this is 1/4 over 2 times, or 1 times 4 over 2 times 18, no? So that will be 1 over 9. And then x times x, that is x squared. So this will now be the shear equation for this segment. Okay, now for the moment equation, okay, we are going to take moment, okay, at the section, no, where we cut the beam. Okay, so this is, this will always be the center of moment. Okay, every time that we take moment here, no, we are going to take moment at the section where we cut the beam. Okay, so that the shear force will be cancelled. Okay, so for the shear, for the moment equation class, yun nga, we take moment class here. Okay, so this will be 30 times its moment arm to this point class. So that will be x. So its moment will be 30 times x, and its rotation will be clockwise. That's why it's positive here. Now for the equivalent point load of the rectangle, so this is 2x. So its moment arm class is x over 2. So this will be 2x times x over 2. And its rotation about the center of moment, which is here, this is counterclockwise. That's why it's negative here. Now, for the equivalent point load of the triangle, okay, so this is 1/2 Wx. So its moment arm class is x over 3. Okay, so this is 1/2 times W, which is 4x over 18 times x, and its moment arm is x over 3. And its rotation class is counterclockwise. That's why it's negative here. Now, for the moment, the internal moment class, this is counterclockwise class. So this will be negative here, ha? Okay. So, solving for the internal moment class, so this is 30x, and then this will be x squared, no? 2 will be cancelled. And then here, this is 1 times 4 over 2 times 18 times 3. So that is 1 over 27. Okay, and then x times x times x, that is x cubed. Okay, so this will now be the equation, okay, for moment. Okay, so we can use these two equations, class, to solve the shear and moment at any distance x, no, for this segment, okay, for this beam. Okay. Okay, so after we establish the shear and moment equations, we can now construct the shear and moment diagram by plotting the equations, no? Okay, so for the shear equation, so this is the shear equation class. Okay, so we are going to solve the value of the shear at x is equal to 0. So for x is equal to 0 class, we just substitute 0 to all the variables x here. So this will be 0. Okay, this will be 0. So what will remain here is the 30 kips. So the shear at x equal to 0 is 30 kips. Now for the shear in x equal to 18, okay, so this is the other end, no, of the segment or the beam. Okay, so we just substitute this 18, no, to the variables x. Okay, so this will become 30 minus 2 times 18 minus 18 squared over 9. So the shear here, class, will be negative 42 kips. Okay, so from here, class, no, we can now graph, no, our these values. Okay, so for x equal to 0, so this is x equal to 0. Okay, so the shear here, class, is 30. So this is positive, so it will be plotted above the x-axis. So this will be 30 here. Okay, and then for the next point, which is at the other end, class, which is 18, x equal to 18 here, class. Okay, so x equal to 18, so this is 42, negative 42 kips, so it will be plotted below the x-axis. So this will be 42. So we have 2 points here. Okay, the shear here, and then the shear here. Okay, so we are going to connect these 2 points, class, no, using our rule. No, so our rule, class, if our loading, okay, if our loading is negative increasing, so this is negative increasing, right? So this is negative because this is downward, and this is increasing. Okay, so if it's negative increasing, class, okay, so our the slope, okay, or our what do you call this? The curve here, class, no, the curve here will be second degree, okay, and it will be or it's parabolic, no, and it will be concave downward. Now that's why it's concave downward. Okay, so this is concave downward. This is concave downward, class. Okay, so that's our rule. So this is really parabolic because from our equation for shear, class, so this is x squared, right? Okay, since this is x squared, so this is second degree. So this is parabolic. Okay, so this will now be our ano no, our graph, okay, or our diagram for shear. Okay, and take note here, class, or notice here that for this graph, no, so it passes the x-axis, okay, at this point. Okay, so let's say at this point, class, no, from the left, okay, so from the leftmost part, okay, so let's say that this is x, so this is distance x. So we don't know yet this value, ha, if what is the value of this x. So this is not automatically x over 2 or 18 over 2, no? So this is not just at the um, mid-span, no? So this, we don't know yet this value. So we are going to solve this. Now, to solve this, class, we are going to use this equation. Now, we know that at this point, class, so this is 0. This is 0 shear, right? So we can determine this x, knowing that the shear here is 0. So we just substitute 0, no, for v here, and then solve for x. And as you can see here, class, so this is 0 is equal to 30 minus 2x minus x squared over 9. So this is parabolic, no? So x squared over 9, since there is x squared here, no? So class, there will be two values of x here. So to solve for those two values of x, you can use quadratic formula. You can use um, uh, what else can you use? You can actually use your calculator then, no? But you can use ano ha, quadratic formula. So recall the formula for that. Okay, and then if you are going to use calculator naman, no, so you can press your calculator mode 5, and then press 3. No, so in this case, x squared over 9. So this is negative 1, 9, no, the coefficient. So for the first value here, negative 1 over 9. And then for the second value, negative 2. And then for the constant, that is 30. Okay, yeah. So the values, class, for x here are 9.734 or 9.7350 and negative 27.7350. Okay, so but here, class, no, we are only going to use the value that is logical. Now, in this case, class, the value of x that is negative, this is not logical, right? So there is no negative distance. No, so instead, class, no, we are going to use the positive value for x. So we are going to use x is equal to 9.7350. So this is the value, no, of this x. So this is the distance x. So this is 9.7350. Okay, so this is the ano, the location of the zero shear. Okay. So from here, class, no, so again, this is already the shear diagram. Now, for the moment diagram, of course, we are going to use the moment equation. So this is the established moment equation, class. Okay. So for this moment, class, okay, so to plot the moment diagram, so we start with x is equal to 0. So we just substitute 0 to all the variables x here. Okay, so this will become 30 times 0 minus 0 squared minus 0 cubed over 27. So in this case, moment is just ano, 0. Okay, and also, class, for we also ano ha, we will also solve, no, for the moment here at this point. Okay, so again, class, we depend our moment diagram to our shear diagram. Okay, so as you can see here, the shear diagram, class, uh, has discontinuity here, no? Since it passes through the x-axis here. So we are going to solve for the moment at this distance. So the distance here, class, is 9.7350. So for distance x equal to 9.7350, okay, so we just substitute this value to the variables x here to solve for the moment, no, at that distance x. So this will become m is equal to 30 times 9.7350 minus 9.7350 squared minus 9.7350 cube over 27. So the moment here, class, will be 163.11 keeps feet. Okay, so be, ano, class, how be careful of our unit. So this is moment. So of course, the unit is keeps feet. Okay, so that will be the moment at this point, ha? Okay, and for the moment, no, at the here, no, so this is x is equal to 18. So we also solve this. We just substitute 18 to all the variables x from the equation, no? So this will become 30 times 18 minus 18 squared minus 18 cubed over 27. So solving for the moment, this is 0. Okay, so we can now plot this, no, in our moment diagram. Okay, so at x is equal to 0, class, the moment is 0. That's why it starts here. Okay, and for the moment, no, for distance 9.7350, so the moment here, class, is 163. 163.11 keeps feet, no, at this point. And then at distance x equal to 18, so at this point, class, the moment is 0. That's why the point is here. So for these 3 points, class, okay, the point here, and the point here, to connect them, class, no, we are going to use our rule here. So we are going to depend, no, the curve here from the shear. Okay, so from the shear, class, from this point up to this point, so our curve here, class, this is sloping down. Okay, so since this is sloping down, class, okay, since this is sloping down, the moment will be sad, right? The moment will be sad. So the curve here will be sad. Okay, from this point up to this point, so this will be sad. The curve will be sad. Okay, and from this point up to this point, the shear, so this is still ano, no, sloping down. Okay, so the curve in the moment, it will still be sad. Okay, so this will be concave downward. Okay, so the curve also here is concave downward because this is sad nga. The moment is sad. Same here. The moment is sad, so it will be concave downward. Okay. So, class, take note that this, ano ha, this curve in the moment, this is already cubic. No? And as you can see in the equation naman, no, this is really cubic. The equation is cubic. Right? Okay. So, from here, class, no, if you are going to observe here or analyze this moment diagram, so the maximum moment here is at this point. This is 163.11 keeps feet. Okay, and the location of this moment, class, is actually at the zero shear. No, so realize that. Okay. Okay, for sample problem number 4, establish the shear and moment equations for each segment of the beam shown. Draw also the shear and moment diagram. So we have here a simply supported beam with um, an applied load P, no, applied here at the midspan of the beam. Okay, so let's solve this. Okay, so to solve this, we are going to start with the computation of the support reactions. Okay, so drawing the free body diagram of the beam. So this will be the free body diagram. Okay, so for this roller support, there will be a reaction here. Okay, and for the hinge here, there will be a reaction here. Okay, so class, to solve for these reactions, class, now we can take moment at B. So we can take moment here so that our B will be cancelled and we can solve for R sub A. So taking moment at B, so clockwise moments will be positive. Okay, so RA, its moment is RA times the moment arm, which is L. No, L over 2 plus L over 2 is L. Okay, and its rotation is clockwise, so it will be positive here. Now for the force P, okay, so its moment about point B is P times L over 2. Okay, its rotation will be counterclockwise, so it will be negative here. So solving for R sub A, okay, so we can transpose this to the other side. So this will become positive PL over 2. And then dividing both sides by L, no, to solve for R sub A. So it will become P over 2. Now for R sub B, so we can just sum up forces vertical here. Upward forces as positive, no, for our convention here. Okay, so this will be R sub A minus P plus R sub B is equal to 0. Okay, so we just substitute the value of R sub A that we solved already. So this will be P over 2 minus P plus R sub B is equal to 0. So solving for R sub B, so this will just be um, P over 2 minus P, this is actually negative P over 2, no? And we just transfer it or transpose it to the other side. So therefore, R sub B is equal to P over 2. So obviously, R sub A and R sub B, okay, so this load P, okay, it will just be divided, no, to the two supports here. Since this load P, this is applied at the midspan. So it will just be divided equally, no, by the support to the support here are at R sub or at the support here at A and the support here at B. That's why they are just P over 2, okay, for both reaction forces. Okay, now the next step here, class, no, is to divide the beam into segments. Okay, so that the loading within each segment is continuous. Okay, so the endpoints, class, of the segments will be the discontinuity of the loading, including concentrated loads or forces and couples. So in this case, class, for this beam class, our first segment will be from this point load or from this concentrated load up to this next concentrated load. Okay, so the first segment, class, will be from here to here. Okay, so the endpoints here, class, are the are the concentrated loads. Okay, so this will be our first segment from here to here. So this is from 0 to L over 2, and our second segment, class, will be from here up to here. So both of the endpoints, class, of this segment, class, are concentrated loads, no? So again, our segment 1 will be from here to here, and our segment 2 will be from here to here. So we are going to solve the shear and moment equations for each segment. Okay, so for the first segment, that is 0 less than equal to x, and then less than to L over 2. So that is from 0 to L over 2. Okay, so we are going to cut, no, a section here at this segment, and then we consider this left segment. Okay, so considering the left segment, class, this will be the left segment. So the reaction here is P over 2. And then the distance, no, from the leftmost part up to the section, no, where we cut the beam. So the distance is x. Okay, and at this section, class, okay, so we will put here the internal shear force, okay, and the internal moment. Okay, so we are going to solve for the shear first, okay, by using summation forces vertical is equal to 0. Okay, so this will be P over 2 minus V is equal to 0. Okay, so from here, class, V is equal to P over 2. Okay, so this will now be the equation for shear, no, from 0 to L over 2. Okay, so and then, class, for the moment, okay, so we are going to take moment at the section here where we cut the beam, okay, to cancel the shear force, no? So summing up moment, class, so this will be equal to 0. Clockwise rotation will be positive. So P over 2, its moment will be P over 2 times x. Okay, and its rotation will be clockwise. That's why it's positive here. And the internal moment, class, this is negative since this is counterclockwise. So solving for m, this is px over 2. So this is now the moment equation. So these two equations, class, no, this shear and moment equations, this will just be applicable, class, for distance x, no, from 0 to L over 2. Okay, from here to here. Okay, Now, for the second segment class, so the second segment class is from L over 2 to L. Okay, from here to here. Okay, so we are going to cut this segment, no, or the beam, no, we are going to cut within the span of this segment. So we are going to cut it here. So we can consider this left segment or this right segment. So if we consider this left segment class, so the distance here class is x, no, from the left up to the section where we are going to cut this segment. Okay, so this is x. So if you are going to consider the right segment class, the distance here class should be L minus X. Okay? Okay. So from here class, no, we consider the left segment. Okay, this segment. So there will be R sub A here, which is P over 2. And then this load P, it will also be included. So this is P, and this is L over 2 from the left. Okay, so again class, at this section where we cut the segment, so this will be distance x from the leftmost part, okay, of the beam. Okay, so at the section class, there will be an internal shear force V and an internal moment M. Okay, so from here class, now we are going to solve the shear and moment equations. So for the shear equation, we are going to use summation of forces vertical is equal to 0, positive for upward forces. So P over 2 minus P, so this is negative since this is downward, minus V is equal to 0. So solving for V, this will just be negative P over 2. Okay, so this will now be the shear equation from this segment or from this point up to this point of the beam. Okay, so this will only be applicable half for the segment L over 2 to L. Okay. Now, for the moment equation, we're just going to take moment at the section where we cut the segment. Okay, so that the shear force will be cancelled. Okay, so the moment of P over 2 is P over 2 times the moment arm, which is X. And then for the P, okay, its moment arm class, it will be, the moment arm will be this distance, right? Okay, and this distance class, this is x minus L over 2. That's why it's x minus L over 2 here. So this is counterclockwise, no? It's rotation about this point. So this is counterclockwise. That's why it's negative here. And for the internal moment, this is also counterclockwise. That's why it's negative here. So solving for the moment, so this will just be px over 2 minus px, negative times negative, that will be positive, pl over 2. So we just, we will just uh, simplify this by, what can we factor out? Actually, it's okay na, no? This will just be px over 2 minus px. Okay, so px over 2 minus px, that is actually negative px over 2. And then for this is pl over 2. So we can factor out p over 2. Okay, we can factor out p over 2. And then this will become p over 2 times negative x plus l. So this will now be the moment equation. So again, class, this shear and moment equations, this will only be applicable half for x from L over 2 to L. Okay, so that will be from here to here. Okay. Okay, so we can now construct the shear and moment diagrams from the equations, no, for shear and moment for each segment that we established from the previous slide. Okay, so we will start with the first segment. So for the first segment, the the distance x is from 0 to L over 2. So for the shear equation class, this is the shear equation. And as you can see, this is equal to P over 2. And P over 2 class, this is actually constant. No, so there's no variable x here. So meaning to say, class, for if x is equal to 0 class, since there's no variable x here, the shear force is P over 2. So this is a constant. Okay? Okay. And also, class, for x is equal to L over 2. Okay, so the shear force is still P over 2 because it's constant nga. No? So now for the second segment, class, so the second segment is from L over 2 to L. Okay, so for the shear equation, okay, for the second segment, so this is V is equal to negative for P over 2. Okay, so for this class, this is also constant. So for x equal to L over 2, okay, the shear is negative P over 2. Okay, and also for x is equal to L, okay, shear is still negative P over 2. So these values of shear class are constants. Why? Because class, our loadings here, no, if you can notice from the loading of the beam, they are concentrated loads. And class, if the loadings are concentrated loads, class its shear, they will be rectangles. And rectangles class are constant, right? So we will plot this in our diagram class. Okay, so class, for the shear diagram, okay, at x is equal to 0, the shear class is P over 2. So P over 2 is positive, no? So it will be plotted above the x-axis. So this is the x-axis. So this is plotted above. So this is the P over 2. Okay, now, for x is equal to L over 2. So L over 2 is at this point, no? So the shear here is uh, still P over 2. So this is still P over 2 since this is constant nga. Okay, now for the second segment, so the second segment is from L over 2 to L. Okay, the shear in L over 2, x is equal to L over 2 class, is negative P over 2. So this is negative shear, so it will be plotted below the x-axis. That's why it's here. Okay, and for x is equal to L, okay, so the shear is still negative P over 2. That's why here at distance L, no, the shear here is negative P over 2. Okay, so we are going to connect this points, no, here, 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 here. No? So they will just be connected by straight lines. So from the origin, no, to the shear here, and then we will connect this to the shear here, and then we are going to connect this shear to the shear here. Okay, and we are going to connect this to the shear here, and we are going to connect this to this point. Okay, so this will now be the shear diagram class. Okay, so this will now be the shear diagram. Okay, so from here, class, now we can now also construct the moment diagram, now using the moment equations. So the moment equation for x from 0 to L over 2, class, is px over 2. Okay, so class, we are going to solve for the moment at x is equal to 0. So we just substitute that 0, no, to the variable x. So this will be p times 0 over 2. So the moment at x equal to 0, class, is 0. Now, we are also going to solve, class, no, the moment here at this point, no, of the from the shear diagram. So this is L over 2. Okay, so for x is equal to L over 2, okay, at this point. So this is, we just substitute L over 2 to the variable x. So this will become P times L over 2 over 2. So this will become PL over 4. So the moment here, no, at the midspan, class, is PL over 4. Now for the moment at, okay, at the second segment, class, so this is the second segment. So this is for distance x, L over 2 to L. Okay, so for x, for this segment, class, no, the moment equation is P over 2 times negative x plus L. Okay, so for x equal to L over 2, class, okay, so we are going to solve for the moment. Okay, so we just substitute this L over 2 to the variable x. So this will become negative L over 2 plus L. Negative L over 2 plus L, class, this is actually L over 2, right? So P over 2 times L over 2, that will be PL over 4. Okay, so this will be the moment, no, at x equal to L over 2. Now, for x equal to L, so that x equal to L is here, no, at this point. Okay, so for x equal to L, class, so we just substitute L to the variable x here. So this will become negative L plus L. So that will be 0, right? So the moment at that point is 0. So graphing this, class, no, or plotting this in the moment diagram. So for x equal to 0, class, this is the moment is 0. Okay, for x is equal to PL, or for x equal to L over 2, class, the moment is PL over 4. Okay, and this is positive, class. So this is at the above x-axis. Okay, so PL over 4 is here. Now for the second segment class, the moment, of course, it should be consistent. Okay, if for x equal to L over 2 class, okay, the moment should still be PL over 4. So this is PL over 4. And then for x equal to L class, the moment is 0. Okay, so from here class, now we are going to use our rule. Now we have 3 points here for moment at this point, and at this point. So we are going to connect these points using our rule. So from the shear, plus our shear here are rectangles, right? So class, the moment here should be triangles. No? And for shear that are constant class, okay, so for positive constant, okay, so the moment class should be sloping up. Okay, it should be sloping up. Okay, and for shear that is negative constant class, it should be sloping down. Okay, so it should be sloping down here. Okay, so these are just straight lines ha. So since the moment should be triangles. Okay. Okay, so this will now be the moment diagram class. And as you can see in the moment diagram, the maximum moment here is PL over 4. Okay. Okay. And this is located at the zero shear also. No? So, also. Okay. Anyway. Okay, but actually class at this point pala, no, this is no ano, no? This is not actually at this point at the left side of force P, no, the shear is this. Okay, P over 2. But at the right side of P, no, the shear class is negative P over 2. Yeah, but anyway, okay. So this will now be the answers class for this problem. Now, for sample problem number 5, establish the shear and moment equations for each segment of the beam shown. Draw also the shear and moment diagram. So, class, for this beam, so this is simply supported. And class, the applied load here, class, is a couple. So, we have an applied couple here at the midspan. Okay? And the magnitude of the couple is 40 Newton meter. Okay, so to solve this class, we are going to solve first for the reactions at the support. Okay, so for the reactions of the support, so this will be the free body diagram. Okay, so class, the applied loading here class is a couple. No, so this couple class is clockwise. No, so this is clockwise. So class, the reaction forces here at A and B class, they should also form a couple that is opposite, no, in direction to the applied couple. Okay, so the reaction here at A and B, again, they should form a counterclockwise rotation. No, since they should oppose, no, the applied couple, which is clockwise. So in this case, class, R sub A should be directed downward, and for R sub B, it should be directed upward, so that they will um, rotate. No, it will form a couple and will rotate counterclockwise. Okay, so this will be the reaction at A and reaction at B. Okay, so to solve for the reaction at A and B, we can take um, moment at B to solve for R sub A. So taking moment at B, okay, R sub B will be cancelled. So the moment of RA class at point P, that will be RA times 3 plus 3. So that is 6, no? Okay, and this will be counterclockwise. That's why it's negative here. Now, for the couple, so this is already a moment class, this couple. So we will just directly um, add this, no, to the summation of moment. But this is clockwise. Now, that's why it's positive here. So, solving for R sub A class, so this will be 6.6667 Newton. So, this will be the reaction at A. Now, to solve for the reaction at B, that will just be summation of forces vertical is equal to 0. So, this will be negative RA plus RB is equal to 0. So, RA is already 6.66667 Newton. So, we can just substitute that here. Therefore, class R sub B is also equal to 6.6667 Newton. So, from here, class, no, we can now um, uh, divide. No? Our next step, class, is divide the beam into segments. Okay, so here, class, from this point, okay, so we have a concentrated load here, and at this point, we have a couple here. So this will be the endpoints of the first segment. From this point, class, up to this point, so this will be the first segment. And from this point up to the another point load here, class, so this will be the second segment. From this point to this point. Okay, so for the first segment, class, okay, again, that will be from this concentrated load up to the couple, the location of the couple. So that will be from 0 to 3. Okay, so we are going to draw the, we are going to cut a section, no, within the span of that segment. Okay, so we are going to cut that here. So this section, class, this is distance x from the left. Okay, and that at that section, class, no, there will be an internal shear force B and an internal moment. Okay, and for this reaction at A, class, of course, we will include that. That is 6.667 Newton. So this is downward, since this is downward here. Okay, so from here, class, we are going to solve the shear equation by using summation of forces verticals equal to 0. For upward forces, it will be positive. Okay, so this will be negative since this is downward minus V. So the equation, class, for shear, this is negative 6.6667 Newton. And as you can see, class, this is constant. Okay, since the load here, class, is just point load or concentrated load. Okay, so the shear will just be constant. Okay. So also, class, for the moment, okay, for the moment equation, we're going to take moment at the cut section, okay, so that the shear force V will be cancelled. Okay, so taking moment at this section, class, so the moment of this 6.6667 Newton is 6.6667 times its moment arm, which is x. And this will be counterclockwise, no? That's why it's negative here. And for moment, this is also counterclockwise, so it will be negative here. So for the moment, class, no, so the value for the internal moment, this is negative 6.6667 x. Okay, so this will be the moment equation, class, for moment at the first segment. Now, class, for the second segment, so our second segment is from this point to this point. So this is from 3 to 6. Okay, so from 3 to 6, class, for the shear and moment, okay, equation. So we are going to draw here first, no, we are going to cut, no, this segment, no, within its span. So let's say we cut it here, and then the distance of this section from the leftmost part of this beam is x. Okay, so we will consider this segment, this left segment. Okay, so again, class, if you are going to use this right segment, so it can, you can also do that, but the distance here, class, will be 6 minus x. Okay, since the total distance here is 6, and then the distance here is x, so this distance will be 6 minus x. Now, if you are going to use the right segment. But in this case, we are just going to consider the left segment. So this will be the left segment. So of course, we have here this reaction. This couple will also be included. Okay, and then at the cut section, class, there will be an internal shear force V and an internal moment. Okay, so to solve for the shear equation, class, summing up forces vertical here. Okay, so this will be negative 6.66667 minus V. Okay, so solving for V, this is negative 6.6667 Newton. So this is also constant, class. Okay. Okay, so from here, class, we can also solve for the moment equation by taking moment at the cut section. Okay, so taking moment at the cut section. So this will be 6.6667 times its moment arm, which is x. And then its rotation will be counterclockwise. That's why it's negative here. Now, for this couple, so this is already a moment, so it will just be included, no, in our summation. So its rotation is clockwise, so it will be positive here. Okay, that's why it's plus 40 here. Now, for this internal moment, this will be negative m since this is counterclockwise. So solving for m, class, so this will become negative 6.66667x plus 4t. Okay, so this will now be the moment equation, okay, for the segment, no, from 3 to 6. Okay, so these equations, class, it can only be applied from 3 to 6. Okay, and these equations, it can only be applied from 0 to 3. Okay. Okay, so we can now construct the shear and moment diagrams from the established shear and moment equations, no, from the previous slides. Okay, so class, for the first segment, that is from 0 to 3, for the shear equation, okay, so this is negative 6.6667 Newton. So class, this shear, this will be constant from 0 to 3. Okay, now for the shear from segment wherein x will be from 3 to 6. Okay, so the shear also here, class, is constant, and this is negative 6.6667 Newton. So this shear, class, will be constant from distance 3 to 6. Okay, so we can directly, or we can plot this now, no, to our shear diagram. So this is our shear diagram, class. Okay, so class, at x equal to 0, the shear is negative 6.6667 Newton. So it will be plotted below the x-axis. So it is below the x-axis. This is the x-axis. So this is below. Now, this will be constant, class, up to distance x is equal to 6. So it will just be constant here. So we will just connect these points, class, from here to here. So as you can see here, this is just this shear is a rectangle, right? Because our applied loading here, class, is a couple. And if you're going to go back, no, to our discussion, no, if the load is a couple, its shear will be constant. Okay, and in this case kasi, class, no, our couple is clockwise, no, clockwise. Okay, so the couple here, class, no, is clockwise. Okay, so for each shear, class, it will really be negative. No, the shear will be negative. Okay, but if the couple here, class, is counterclockwise, okay, so the shear will be positive. Okay, okay. But in this case, class, no, we can now proceed to the moment diagram. Okay, so for the moment diagram, so we will start with the first segment that will be from 0 to 3. Our moment equation for the first segment is negative 6.6667 x. So for x equal to 0, the moment is also just 0. Okay, and for x equal to 3, class, the moment is negative 6.6667 times 3. So that will be negative 20 Newton meter. Okay, now for the second segment, okay, for the second segment, class, from 3 to 6, no? So the moment equation is negative 6.6667x plus 40. So for x equal to 3, class, so we just substitute the x, no, to the variable x here. So the answer here, class, is 20 Newton meter. So this is positive. Now for x equal to 6, class, okay, so the moment here will be negative 6.6667 times 6 plus 40. So this will be 0. Okay, so we can plot this now, no, to our moment diagram. Okay, so class, at x equal to 0, the moment is 0. Right? For x equal to 3, no, from the first segment. So the moment, class, is negative 20. So since this is negative 20, it will be plotted below, no, below the x-axis. That's why it's here. Okay, now for the second segment, okay, the moment at x equal to 3, class, that is 20 Newton meter. Okay, and for x equal to 6, the moment, class, is 0. Okay, so class, we have here this point, this point, this point, and this point. Now, to connect these points, class, okay, so we are going to use our rule. Again, class, for this, no, if the shear is a rectangle, of course, the moment, no, it should be triangle. So this point, from this point up to this point, it will just be a straight line. Okay, so to form a triangle. Okay, and from this point, class, up to this point, so this will also be just a straight line. Okay, since our shear is a rectangle. So therefore, our moment will just be triangles. So this will now be the moment, shear and moment diagram, class, have for this problem. Now, for sample problem number 6, establish the shear and moment equations for each segment of the beam shown. Draw also the shear and moment diagram. So let's solve this, class. Okay, so for this problem, class, we have here this simply supported beam. Okay, and it carries this uniformly distributed load, no, with intensity 8 kilonewton per meter. And it also carries this concentrated load 15 kilonewton. Okay, so to solve class, no, the shear and moment equations and to construct the shear and moment diagram, we will start with the computation first, no, of the support reactions. Okay, so for the free body diagram class of this beam, so since this is supported by a roller here, so there will be a reaction here. And since this is supported by a hinge here, so there will be a reaction here. Okay, so from here, class, we can solve for the reactions R sub A and R sub B. So let's first take moment here at point B so that R sub B will be cancelled, and we can solve for R sub A. So R sub A, its moment, class, will be RA times 4 plus 3 plus 3. So that will be 10. 4 plus 3 plus 3, that is 10, no? Okay, and its rotation about point B will be clockwise. That's why it's positive here. Now, for the rectangular load, okay, so solving its equivalent point load, class, so that will just be the area, no, of this rectangle, which is 8 times 4. Okay, so 8 times 4, and then the location of that concentrated load, class, will be at the center of 4 meter, which is 2 meters, no? So that will be its moment arm, therefore, of that equivalent point load about point B, that will be 2 plus 3 plus 3. So that will be the moment arm, ha? And its rotation, class, will be counterclockwise about point B. That's why it's negative here. Now, for this 15 kilonewton concentrated load, its moment will be 15 times 3. And its rotation will be counterclockwise. That's why it's negative here. So, solving for R sub A, class, so this will be 30.1 kilonewton. So, we can now solve for R sub B by taking a force as vertical. So, this will just be R sub A minus the equivalent point load of this rectangular load, which is 8 times 4, minus the concentrated load, which is 15, plus R sub B. So we just substitute the value of R sub A that we already solved. So solving for R sub B, this is equal to 16.9 kilonewton. So from here, class, no, we can now divide the beam into segments. Okay, so that is our next step, class, to solve for the shear and moment equations. So here, class, no, so for the first segment, from this point up to this point, no, it has this continuous loading, no. So this loading starts here and then it continues up to this point. Okay, so that will be our first segment from this point up to this point. Now for the second segment, okay, so from this point up to the location of the concentrated load, that will be our second segment. So from this point to this point will be our second segment. And then for the last segment, class, that will be from the concentrated load, okay, up to the another concentrated load, which is here. Okay, so that will be our third segment. Okay, so for the first segment, class, okay, so that will be from 0 to 4. Okay, so we are going to cut, no, that segment. So any section here, no, within the span of the first segment, we are going to cut. Okay, so this will be the free body diagram, class. So at the cut section, class, okay, so the distance from the left is x. Okay, and then of course we are going to include this reaction at A, which is 30.1 kilonewton, and also the distributed loading, we are also going to include this. So the distributed loading here, class, is 8 kilonewton meter pa rin, ha, since this is a constant or uniform loading. Okay, so from here, class, no, we are going to, of course, at the cut section, there will be an internal shear force V and an internal moment M. Okay, so solving for the shear equation, we are going to use summation of forces vertical. So this will be 30.1 plus the equivalent point load of the rectangular load is just the area, no, of the rectangle, which is 8 times x. So that will be 8x here. So this will be negative since it will be downward. Okay, and then the shear force, that is downward, so this is negative. So solving for the internal shear force V, so that will be 30.1 minus 8x. So this will be the equation, class, okay, for shear okay, for the first segment. So this will only be applicable for the first segment. That will be from 0 to 4. Now, for the moment equation class, we are going to take moment at the cut section. Okay, so the moment of 30.1 class, no, about this point, so that will be 30.1 times x, and it will be clockwise, ha. And then for the uniformly distributed load here, its equivalent point load is 8x, okay, and the position class or the location of that equivalent point load will be at the midspan, no, which is x over 2. No, so the moment arm therefore here will be x over 2, and it will rotate counterclockwise. That's why it's negative here. And then minus m. Okay, so solving for the internal moment here, class, so this will be equal to 30.1x minus 4x squared. So this will now be the moment equation, class, okay, for the first segment. Okay, now for the second segment, so that will be from 4 to 7. Okay, so this will be the second segment. So we are going to cut a section, no, within the span of this second segment. And we are going to consider this left segment. Okay, so from the cut section, class, okay, so that will be distance x, no, from the left. Okay, so for this free body diagram, class, no, of the left segment, okay, so of course there will be R sub A here, it will be included. And also, this 8 kilonewton per meter uniformly distributed load, it will also be included. And this is 4 meters, no, the that distributed loading. Okay, and there will be an internal shear force V, no, and internal moment at the section, at the cut section. So to solve for the shear force, class, okay, summation of forces vertical. So this will be 30.1 minus the equivalent point load of this rectangular load, that is 8 times 4 minus V. So solving for V, class, this is negative 1.9 kilonewton. And as you can see here, class, no, the equation of shear here, this is constant, right? So this is constant. Okay. Okay, so from here, class, we are going to solve the moment, no, by taking moment at the cut section. So the moment here, class, will be 30.1 times its moment arm, that is x. Okay, and it's clockwise, no. And then for 8 kilonewton per meter distributed load, so for its equivalent point load, that is 8 times 4. And its moment arm, class, so the equivalent point load, class, that is, no, 2 here and then 2 here. So the moment arm, class, no, of that equivalent point load about this point here, so that will be x minus 2. So for this distance. Okay, so again, for this distance, that is x minus 2. Okay, and then minus m. So solving for m, so this will be 30.1x minus 32x, and then negative times negative, that will be positive, 8 times 4 times 2, that will be 64. So we can combine this further, no, 30.1x minus 32x, that will be negative 1.9x. So this will now be the equation for moment for the second segment. M is equal to negative 1.9x plus 64. Okay. Okay, so for the third segment, this will be the third segment from here to here. So that will be from 7 to 10. Okay, so for this segment, class, no, we are going to cut a section here. Okay, so we are going to consider the left segment. Okay, so this will be the free body diagram of that cut section, no, and we consider the left segment. Okay, so the distance, class, of the cut section from the leftmost part of the beam, class, that will be x. Okay, so it will be or 30.1 kilonewton, that is the reaction at A, no? So it will be included, of course. And the distributed load here, which is 8 kilonewton per meter, it will also be included. So its length is 4 meter, no? And then this 15 kilonewton force, class, no, it will also be included, ha? In that free body diagram of that segment. Okay. So from here, class, no, at the section, there will be an internal shear force B and an internal moment M. Okay, so we are going to solve the shear and moment equation. So for the shear equation, using summation of forces vertical, Okay, so this will be 30.1 minus the equivalent point load of the rectangular load, that is 8 times 4, minus the point load here, which is 15, and then minus the shear. Okay, so solving for shear, this is negative 16.9 kilonewton. So this is constant, no? So this is the shear equation class half for x from 7 to 10. Okay. Now for the moment class, so we will take moment at this section. Okay, so taking moment at that section class. So the moment of 30.1 about this point will be 30.1 times its moment arm, which is x. Okay, and for the equivalent point load, its moment arm class will be x minus 2. No? So that will be 8 times 4 times x minus 2. And that will be counterclockwise. And then for this 15 kilonewton concentrated load, its moment arm class will be this distance now. And this distance is x minus 7. Okay, so that will be x minus 7 here. And then for the moment, that will be negative m. So solving for m, okay, so this will be 30.1x. And then for this, negative 8 times 4 times x, so that will be negative 32x. And then negative 8 times 4 times negative 2, that will be positive 64. And then negative 15x, no? And then negative times negative, so that will be positive. 15 times 7 is 105. So that will be for m, no? Okay, so we can simplify this further by combining like terms. So combining like terms, that will be 30.1x minus 32x minus 15x. That will be negative 16.9x. And for the constant, 64 plus 105, that is 169. So this will now be the moment equation for segment from 7 to 10. Okay. Now we can start plotting the shear diagram class. Okay, so for the shear diagram, okay, from 0 to 4, so that will be for the first segment, our shear equation is 30.1 minus 8x. So for x equal to 0, okay, the shear will be 30.1 minus 8 times 0, so that will be 30.1 kilonewton. Now, for x equal to 4, the shear will be 30.1 minus 8 times 4. So that will be negative 1.9 kilonewton. Okay. And also, class, for the second segment, that is from 4 to 7. Okay, so the shear equation here is negative 1.9 kilonewton. So it will be constant from 4 to 7. This is the shear. Now, for the third segment, that is from 7 to 10, the shear also here, class, is constant, and that is negative 16.9 kilonewton. Okay, so plotting this values, class, no, for shear. Okay, so at x is equal to 0, class, the shear here is 30.1. That is positive, so it will be above the x-axis. Okay, so this will be 30.1. For the next point, that is x equal to 4, so that will be at this point. Okay, the shear here is negative 1.9. That's why this is plotted below the x-axis, no? So this is negative 1.9 here. Okay, so this is negative 1.9. So we already have 30.1, and then for x equal to 4, this is negative 1.9. And for the second segment, class, no, the shear is negative 1.9. So of course, it has to be consistent here. So this is negative 1.9, and up to x is equal to 7, which is at this point. So this is constantly negative 1.9. Okay, so this is also negative 1.9 the shear here at x is equal to 7. Now, for the third segment, class, the shear at x is equal to 7, which is at this same point. Okay, so at this same point, class, no, the shear is negative 16.9. Okay, so x equal to 7, class, negative 16.9. So negative 16.9 is somewhere here. Okay, and then this is constant up to x is equal to 10. No, so this will be constant. So at this point, class, this is negative 16.9 also. Okay, so class, we are going to connect, no, those points. So we have this point, this point, this point, this point, this point. Okay, for shear. Okay, so for these points, let's say for the first segment, so the point here is this point, and this point. So to connect these points, class, so we will uh, base that, no, on the loading. So the loading here, class, is a rectangle. So the shear must be triangle. Okay, and class, the load here is negative constant, right? So for negative constant, class, the shear will be sloping down. So of course it should be sloping down, and it's just a straight line, class, ha, since this is just a triangle. Okay, now for the next point, so here to here, so this is just constant, so this will just be a straight line. Okay, and from here we just connect that point, this point to this point. No, we just connect them, and then from this point up to this point, so this is just constant, so this will just be a straight line. Okay, so from here, class, no, this will now be the shear diagram. And as you can see here, class, no, for the shear in the first segment, okay, so this straight line, class, no, passes through the x-axis at this point. So we are going to solve this value of x because we are going to use this, class, no, for plotting the moment. No, so we are going to solve this distance x, no, at this this is zero shear here. Okay, so we are going to solve for this value of x. Okay, so to solve for the value of x, class, so the shear here is 0. So we are going to use the shear equation, no, for the first segment. So this is the equation for the first segment. So that will be, okay, the shear is 0 equal to 30.1 minus 8x. So solving for the value of x, so this will be 3.7625. So this will be the this distance x. From this point up to the zero shear, this is 3.7625. Okay, so we already plotted now, no, the shear diagram. Now for the moment diagram, okay, so we will start with the first segment. So for the first segment, class, the moment equation is 30.1x minus 4x squared. Okay, so this is the equation. So expect a parabolic graph here, no? So since this is the equation of the moment. Okay, so for x is equal to 0, class, the moment is 30.1 times 0 minus 4 times 0 squared. So the moment is just 0. Okay, so for moment, for x equal to, okay, so class, this is the this is the distance x. Okay, so we are going to solve also for the moment at this point because this is where we can find the maximum moment. Okay, so for x equal to 3.7625, the moment here, class, will be 30.1 times 3.7625 minus 4 times 3.7625 squared. So this will be 56.626 kilonewton meter. Okay, so for x is equal to 4, so the moment, class, is 30.1 times 4 minus 4 times 4 squared. So the answer here is 56.4 kilonewton meter. So as you can see here, no, so the values for this moment and this moment, they are close, no, since the distance here are close also, no. Okay, so that will be the moments, no, for the first segment. Now for the second segment, so that will be from 4 to 7. Okay, so the moment equation here is negative 1.9x plus 64. So for x equal to 4, the moment is negative 1.9x or 1.9 times 4 plus 64. So the moment is 56.4 kilonewton meter. Now for x equal to 7, the moment is negative 1.9 times 7 plus 64. So this will be 50.7 kilonewton meter. Now for the third segment, class, so the moment equation is negative 16.9x plus 169. For x equal to 7, the moment is negative 16.9 times 7 plus 169. So the moment is 50.7 kilonewton meter. Now for x equal to 10, the moment is negative 16.9 times 10 plus 169. So the moment is 0. Okay, so plotting these values, class, no, in the moment diagram. Okay, so for the first point, class, that is x equal to 0, so the moment here is 0. Okay, so this will be here. And then for x equal to 3.7625, so that is at this point. Okay, so the moment here, class, is by 56.626 kilonewton meter. Okay, and then for x equal to 4, so the distance 4 is here, no? So that will be 56.4. So it will go down a little bit, no? Okay, and then for x equal to 4, so that is the same now, 56.4. For x equal to 7, 50.7. So x is equal to 7 is here at this point. So this is 50.7. And then for x equal to 7, no, for the third segment, that is still 50.7. And then for x equal to 10, okay, for x is equal to 10 plus, the moment is 0. So therefore, the point is here. Okay, so we are going to connect those points, class, ha, using our rule. Okay, so for the first point, this is the first point. The second point is here. So to connect these 2 points, class, we are going to base that to the shear. No? So based on shear, so this is sloping down, right? So this is, the shear here is sloping down. Okay, and class, the shear here is a triangle. Therefore, the moment, it should be parabolic. Okay, and class, since the shear is sloping down, okay, so class, the moment will be sad. Okay, so it will be concave downward. So we connect these 2 points concave downward by this curve concave downward. Okay, and also class, from this point to this point, okay, so this is still sloping down. Okay, the shear is still sloping down. So the moment will also be sad. No, so it will be concave downward. So it will be concave downward here. Okay, and from this point, class, up to this point, so this is constant. No, so this is constant. So this is negative constant. So the moment here, class, will be sloping down. Okay, and this is just a straight line, class. It will just be straight line. Okay. Okay, and also for this segment from here to here, so the shear here is a rectangle, no, and this is negative constant since the shear is below the x-axis, so negative constant. So the moment here, plus, will be sloping down, and this will just be a straight line, no, to form a triangle. Here also, there will be a triangle here. It will form a triangle. Okay. So class, now this will now be the moment diagram. Okay, for this problem. So this is the shear and moment diagram. Okay. So that concludes our discussion for this topic. I hope that you learn and attain the learning outcomes. And class, see to it that you do the CM assessment task for this topic. So it will be submitted on our next meeting. Okay, so see you again, class, on our next meeting, and keep safe. God bless. Bye-bye.